Now let's look at a different kind of oscillator, which is a simple pendulum, like we see here. Uh, what I want you to notice is that as a simple pendulum swings back and forth, it's accelerating back and forth. When it's on the right side, it's accelerating back to the left and vice versa. That indicates that there is a restoring force that acts on the bob of the pendulum. The bob means the small mass. And that restoring force is what's causing it to accelerate back, always restoring it back to the vertical position. Second thing to notice is that not only does it accelerate back towards the center, there's also some acceleration towards the center of the arc that it's swinging in at the top here. And that's the centripetal acceleration. Remember that whenever something moves in an arc of a circle, it's also accelerating in towards the center of the circle. So our job is going to be to figure out, to calculate the exact nature of that restoring force so we can then predict what the frequency of the pendulum is. So to do that, let's start with a sketch. Here's the vertical line. Here's where the very light string of the pendulum is attached at. And what makes it a simple pendulum is the string is super light, and the only mass there is really is just in the bob, which is like a point, a particle at a point. Theta is the angle that the bob is at this particular moment. And our job is basically to figure out the forces. So we use a force diagram. The weight of the bob pulls straight down towards the earth. But that force straight down towards the earth actually has a component which is along the arc that the pendulum's swinging on. Here's the arc. It's kind of like being on an incline. Even though the earth pulls you straight down towards the center of the earth, there's a component of that force that acts along the slope itself. How big is that component? That's what we care about. Okay, well, first let's look at this component of mg. Mg has a component away from the center of the pendulum. Notice that if this is angle theta, then so is this. And so this component here, it would actually be mg cos theta. Mg is the hypotenuse of the triangle, and this is the base of the triangle, adjacent to the angle theta. And there's a component here of mg, which is the one we really care about, and that one has magnitude mg sine theta. Okay, so there is a restoring force that acts along tangential to the arc it swings on, which is mg sine theta. Notice that when theta is positive, the force is pulling it back in the negative direction. So in fact, the force is really minus mg sine theta. When theta is positive, the force is negative. When it's on the other side and theta is negative, the force is actually positive, always restoring it back to the zero position, the equilibrium position. Okay, now this restoring force is a bit complicated because it involves sine of theta. Sine of theta is a bit of a complicated function. What I mean is, how do you calculate sine of theta? Or not how do you do it, but how does your calculator compute sine of theta? It does it with a power series. Sine of theta, when theta is in radians, is equal to theta minus theta cubed over 3 factorial. And there's theta to the 5th terms, and on and on. It's an infinite power series. That's how your calculator computes the value of sine theta. Likewise, cos theta. Cos theta is 1 minus theta squared over 2, and so on. However, if theta is very small, then theta cubed is super small, and you might as well ignore it. So for very small angles, sine of theta can be approximately written as just theta. Remember, this only makes sense in radians. Sine of 5 degrees is not approximately 5. That makes no sense. It works, however, when you plug in theta and radians. And a cos theta is very nearly just 1 for very small angles. And we call these the small angle approximations. When are they valid? When theta is small, small meaning about less than 10 degrees. Okay, so the actual amount of restoring force depends on mg sine theta. However, if the pendulum only swings through a small angle, we can greatly simplify the problem and use the small angle approximation. Okay, we need another mathematical fact, which is the length of this arc. In other words, when it's out at angle theta, what position is it at? Is it at along the arc? Let me call that distance x. So we need the arc length equation, which is that x is equal to L, that's the radius, the length of the string, times theta. That's not any kind of small angle thing, that's just the length of an arc of a circle. Okay, so with that, we'll be able to write down Newton's law. Newton's law says that the mass times acceleration in the x direction is equal to the net force in the x direction, which is just minus mg sine theta. However, for small angles, minus mg sine theta is just about minus mg theta. So I'm going to assume our pendulums only swing through small angles, and so I can make that approximation. I'd like to write theta in terms of x, since I'm working with the acceleration in the x direction. And so I plug in the arc length equation, and this becomes minus mg over L times x. And notice now what we have. We have that the acceleration in the x direction is just equal to, and the mass cancels out, it's equal to minus g over L times x. So the acceleration in the x direction is just proportional to the displacement in the x direction. That's just like a spring, right? The more the spring is stretched out, the bigger it's accelerating back towards zero. Apparently the pendulum works exactly the same way, but only if, it's a small angle of displacement. Okay, now what that's telling me is that this thing is a simple harmonic oscillator. Let's see that. Let's compare it to what we know about simple harmonic motion in general. In general, a simple harmonic oscillator obeys the rule that its acceleration is minus omega squared times x. And therefore, what I've learned is that our pendulum has a value of omega squared, which is g over L. In other words, for the simple pendulum, its omega value is the square root of g divided by L. Meaning that the longer the pendulum is, the lower its frequency is. Or in other words, bigger, longer length pendulums swing more slowly. They have a longer timing as they swing. That's a simple pendulum, and we can predict what its frequency is and what its period is. More general, what if it's not just a tiny little point mass on the end of a light string? What if it's some kind of shape attached to, a pivot? So the shape I'm going to draw is, I'm going to draw it like some kind of a spatula type shape, like this. What if I take something that has a shape like that, I pivot it at the end and let it swing back and forth? It's not a simple pendulum. The mass of this thing is spread all throughout its volume. So I can't just copy this equation to predict its period. What I can do, though, is remember that it does have a center of mass point, which is like here. There's its center of mass. And I could measure the distance from the pivot point to its center of mass. We call it d in these problems. It's like L for the simple pendulum. We might think maybe it's just g over d to get the frequency. That turns out to be not correct because that does not account for the mass being distributed, the inertia being distributed all throughout the object. The right way to handle it is we have to use the torque method. We have to write down the torque on the object to solve this problem. So here's the vertical line. That's the equilibrium position of it, where it would just hang. Now, the weight of this object pulls straight down from the center of mass. So there's mg. Of course, that has a component along the arc that it swings on, which is like here, and that's mg sine theta, just like we saw before. In fact, for small angles, here's theta. For small angles, that's going to be about minus mg theta. So I've used the small angle approximation already here. Okay. This force is the component perpendicular to the line D. So I'll use the torque method now. Torque method says the inertia of the object multiplied by its angular acceleration, this is I, the rotational inertia, multiplied by alpha, the angular acceleration, is equal to the torque. Torque is found from D multiplied by the force. So that gives me minus mgd theta. So notice I had to account for D, the center of mass position, and I have to know how to calculate the inertia of the object. I'll review those things in an example later. So what do we have here? Does this thing follow simple harmonic motion or what? Well, let's see. This tells me alpha is equal to minus mgd over I times the angle theta. That looks a lot like the simple harmonic motion equation, which says that the acceleration is equal to minus omega squared times x. In this case, it's linear position and linear acceleration. Here, it's angular position and angular acceleration. But my conclusion is that, yeah, this thing is a simple harmonic oscillator. It's just that I can read off the value of omega squared, or the value of omega, must be equal to the square root of mgd over the inertia. In practice, how is this used? You could have some object, some part that's been machined, which is a complicated shape. You need, for some reason, to know what its moment of inertia is. So you let it swing like a pendulum, measure the frequency of it, and then you can solve for the inertia and figure out what its inertia is. So that's the frequency of a not a simple pendulum, but a what we call a physical pendulum, which is more than just like the bob on the end of a string. Okay, let's do an example. This L-shaped pair of rods pivots on the end of this wedge. It is a pendulum because its center of mass point is somewhere below that corner. And so if I displace the L shape, here's the L, if I displace it slightly, now the center of mass is off center and it'll swing back. Its inertia will carry it through and it'll go back and forth and wobble, vibrate back and forth. It's not it's not a simple pendulum, obviously. However, it is a physical pendulum. So that's really step one of this problem. I've identified it as a physical pendulum. That means I know that its angular frequency omega, which is 2 pi f, it's going to be equal to the square root of mgd over the inertia. Now, I got to be really careful because m is the total mass of the object. They've chosen m already as the mass of each rod. Okay, so I better be careful and not call that little m, but give it a better name like maybe capital M. indicating this it's the total mass of the whole thing. Okay. So that tells me the frequency. However, I'm not done because I have to plug in m, the total mass. That's easy. I have to figure out the distance to the center of mass from the pivot, and that's not so easy. And the inertia of this shape, I have to figure it out too. Okay, so first of all, m is 2m. That's easy enough. What about the distance to the center of mass? Well, I have to review how to calculate the center of mass position of a shape. I'm going to put the L shape on its side to do the calculation. Okay, so this is the x-axis. This is the y-axis. I need to figure out where exactly the center of mass point is. It's not going to be above L equals L over 2. This rod alone is the center of mass at L over 2. But when you consider the other mass, it shifts the center of mass closer to the corner. Okay. So now reviewing how to calculate center of mass. To do center of mass, what you do is take the total mass of the object and you multiply by the location of the center of mass, which is here. I don't know, I'm just going to solve for that. So x is unknown at this point. It's equal to the mass of each part multiplied by the position of each part, plus the mass of the second part times the position of the second part, and so on. In our object, there are only two parts, so only two terms. Okay, so now we plug in. Notice this is kind of like momentum, where to figure out the total momentum of the system, you add the mass times velocity of each projectile. Here it's mass times position to find the center of mass of the whole thing. Okay, so m is equal to 2m. X is unknown. I'm trying to solve for its center of mass. The mass of each part is just little m. And what's the position of the first rod? Well, it's at L over 2. Its center of mass is at L over 2. The mass of the vertical part is m. Where is its center of mass? Well, it's at x equals 0. So that lets me solve for x. The x-coordinate of the center of mass, this L shape, it is equal to L over 4. Like I said, its center of mass is not at the center at L over 2, it's somewhere above L over 4. Now, the y-coordinate is going to be, by the symmetry of the shape, I know the y-coordinate of the center of mass is going to be also at L over 4. That's going to be equal to the y value by symmetry. I need to know the distance d to the center of mass. So d is going to be equal to x squared, the square root of x squared plus y squared. I plug in the x and y values, and it simplifies to be L divided by 2 root 2. That's how far the center of mass is from the corner. That's the value of d that belongs here. Okay, so I've got m, and now I have d, and the third ingredient, I need to know the inertia. That's easier. The inertia of an object is just the sum of the individual parts. So it's just I1 plus I2. These are both rods pivoted at their endpoint, and so they each have an inertia which is 1/3 ml squared. So I add both of them up and I get 2/3 ml squared. And there it is, that's my inertia, that goes here. And then we plug all three of those pieces in to get the frequency of this physical pendulum.